Observations either at immediately downstream of the dam or immediately upstream of the dam are for things like splitting the watershed model variables into water quality model variables. But the actual load, kilogram nitrogen per day, is straight from the watershed model.
And again, keep in mind that, you know, the G fractions, nobody's measuring that, they're measuring the total.
And what we do is, in the absence of any other information, this is exclusively for the Susquehanna River, where we have a reservoir immediately upstream, it scours, and so on and so forth. In the absence of any other information, for the other rivers, we just use this FLPO that came from the study that was done in the Susquehanna. We use that one. But without this correction for flow, we use the FRPON without the correction for flow, and FG3 is the difference. So we take effectively the values that were determined for the Susquehanna River at normal to low to normal flows, and we use them in all the other rivers. Okay.
I'm sorry, FG2, oh, that's the, so the fraction of G1 is this new constant, FLPON, times whatever is coming out of the watershed model, corrected for flows over 6,500. The FG2 is the same, basically the same thing, and FG3 equals 1 minus FG1 minus FG2. That should be an equal sign, it's double minus. And that's it. Okay. Okay. And how does the watershed model itself account for the scour in Conowingo Dam?
So it is a function of flow.
Period. Okay. So it's in the watershed model.
Yep. So it has it calculates shear stress
Got it.
and. Yep.
So the Conowingo reservoir is not in the hydrodynamic, like receiving model. It's in the watershed.
Yeah, our world stops at Conowingo Dam. Okay, next slide. Okay. Okay, so now we have to do a routing of phosphorus. And as I mentioned, what we do is we take these two watershed model variables, the organic phosphorus and the watershed PIP, we pool them. And then, as with nitrogen, we remove the phytoplankton phosphorus. Now actually, like I said, we're not reducing the load, it's just it comes in implicitly with the algae. Okay, so it haven't really reduced the load. Next thing we got to do is we split dissolved and particulate, and then we split the particulate into inorganic and organic, and when you get to the organic, you've got the three, the labile, refractory, and G3. And just as we had those relationships for nitrogen, I don't think I have them here, but there are analogous relationships for that's going on down. All right, there are analogous relationships for phosphorus. They aren't identical to that, but you know, effectively it's the same thing. It's a constant until you hit 6,500 cubic meter per second, then the G1 and G2 fractions diminish. So, and you know, it's in this drawing, it's in your text. So yeah, there's a lot. So you see, there's a lot of splitting going on here. Dissolved versus particulate, and that comes from observations at the most upstream monitoring station. PIP versus POP, those are actually based on observations upstream of the dam. And then the reactive class is relationships analogous to organic nitrogen. That figure, I showed that either yesterday or the day before, that PIP is a lot of the particulate phosphorus. I think around 40% of what comes over the dam at Conowingo, if the particulate, about 40% of it is this inorganic form. So it's a lot. Okay,
So that's the really non-reactive stuff because it's your PIP.
that's correct.
Okay.
Page down, organic carbon. Okay, as I mentioned, the watershed model has no carbon variable, and yet carbon, the water quality model revolves around carbon. So what we do is we take ratios to organic nitrogen. And basically speaking, that ratio is about 8 to 1. You know, and it's not that different from the composition of phytoplankton or the composition of organic matter in general. And those are based, we didn't pull that out of anywhere. Those are based on this monitoring either downstream, immediately downstream of the fall line or immediately upstream of the fall line. In the absence of any other information, we split the carbon in the same way that we split the nitrogen, which is probably reasonable. And once again, you know, it's the same thing. We need dissolved organic carbon in the 3 reactive classes, so it's analogous to nitrogen. The major thing is that that since this doesn't exist in the watershed model, you know, we had to create it, if you will. And once it's created, treating it is pretty routine. Okay. I guess I won't talk, I'm not going to go into details about how to process these things, but there are other loading sources. Point source loads, you know, treatment plants and industries and such, shoreline erosion, atmospheric deposition. Go ahead.
Quick question if I can on the point source loads. I assume you don't split, or do you split those into the same, for the particulate portions of nitrogen? Do you split them the same way, G1, G2, G3, or just G1, G2?
Jim, I don't recall.
Okay.
We can look in a minute or two, but I just don't recall. The point source loads are really, boy, what's the word I want to use? We don't have anywhere near the comprehensive data set for rooting those into water quality model variables that we have for the fall line and such. Okay, and I think going way back to our original study about 1990, we had some surveys of treatment plants, and by guess or by golly, we pulled out some numbers, and we've probably been using them ever since. But you know, you just don't have that beautiful data set that you have for the fall line. On the other hand, you know, the direct point source loads to the bay are relatively small, so you know, we won't. We'll let it go at that. Shoreline erosion. I talked about this, I guess, a day or two ago. The loads from the shoreline erosion are really big and they're largely inert. But when you go out to the bay and you take a total phosphorus sample, all right, there's no way you can match using a mass conservative water quality model. There's no way you can compute the total phosphorus in the bay if you just use loads from the watersheds and the point sources. You can actually imply this phosphorus coming in from somewhere. And we used to treat these shoreline erosion loads as a separate entity, and recently they've been pulled back into the watershed model. They've been pulled back into the watershed model so that municipalities can get credits for controlling shoreline erosion. I won't go much further than that. Atmospheric deposition to water. I get that from the EPA. Where does EPA get it? We'll have to have another class and we'll teach there. But I'll just say that the EPA gives me the loads directly to the water surface. Now, there's like 11,000 of them because there's 11,000 surface cells, and they're given to me on a daily basis. So you can guess this gets to be a big file. But these are things we deal with. So in any event, we won't go into detail. We'll just say these things exist.
So the atmospheric deposition to water surface, does it apply to CMP or only nitrogen?
CNP,
Everything?
yeah.
Yeah, I know EPA has a network, like monitoring network.
Yeah, as I say, it's just black box to me. But I mean, they don't. Oh Lord, this is funny. They don't pull it out of the air, right? I mean, they get it from somewhere.
They
And,
have a model.
yeah, that's right. Yeah.
Yeah.
Okay.
Yeah, because we use some observation results.
So just real quickly, it's a regression model of observation and then for wet deposition, and then CMAC supplies the dry deposition. And yeah, that's right. So we just put those together.
Okay.
I hope I don't hate myself for what I'm about to do, but okay. So in the material that you downloaded for class, you have the exact software that we use to create water quality model inputs from the watershed model. So somewhere you'll have your program is called make_NPS load _P6, and you can see I created that on June 22, 2017. And you'll also have a make NPS loads.input, and you should have a watershed model 57K, whatever. The watershed model 57K, that's what Gopal gives me. So 57K is, I guess, 57,000 cells, and that's for the year 2001. The make NPS loads.input tells the processor, it provides the splits and that sort of thing. We'll look at it in a moment. So it provides the details as to how to split that file, WSM 57K, and we create the WQM NPS. So that's the actual water quality model file. So if we, I may have this one opened already. Let's see. Yeah, I was looking at this earlier today. So here you go. So the way this one works, basically, the number of cells, the watershed model loads a total of 2,358 water quality model cells, because it actually loads every cell along the perimeter of the bay, not only the big, the fall lines. So what we do is we assign parameter values to a general set of parameter values. And I won't go over every one of these, but you can see, for example, the carbon to nitrogen. Remember, we said that was about 8. The fraction of dissolved organic nitrogen, and this generally, I claim it's 70%. After we take out the 70% dissolved, the remainder 15% is labile, 45% is refractory, and by if you take 1 minus labile minus refractory, the remainder is G3. Similarly, you see over here some fractions for dissolved, labile, refractory phosphorus, and PIP to PP. That's the ratio of 60%. I claim 60% of the particulate phosphorus is inorganic. So,
where's the other 5% of the nitrogen?
Okay, the way it works is 70% is dissolved, so we take off 70%. Yeah. Of the remainder, 15% is labile, 45% is refractory, so that's what, 60, so 40% must be G3.
But doesn't that, I see, I'm sorry. You don't calculate that, I was looking at the FP. Got it.
Okay, so
you're just doing it by difference in the model, so they shouldn't add up to 100. Gotcha.
Carl,
yeah,
I have a question. It looks like everything is based on organic nitrogen, like the splitting and the estimation of carbon is also based on nitrogen. is there any reason why not using organic phosphorus? Is that because organic nitrogen is more, like data is more reliable, or?
Why not have taken your organic phosphorus and use that as your basis for estimating the carbon rather than?
Oh,
Right.
And the reason is because the carbon nitrogen ratio is
Is more
better
stable.
fixed, more stable than carbon and phosphorus.
Okay, that's what I, just wanted.
what we do after that is, so we have this general set of distribution parameters or splits. What we do then is for individual fall lines, we say there are 3 cells which receive inputs from the Susquehanna River. These are the cells. And then this is the set of splits that we're going to use for those 3 cells. So we apply a general set to all of them. Then we come back and say, okay, we have a couple of places where we have better information or different information. So now we use these splits for the Susquehanna River. The Potomac River, there's one place where the Potomac comes in, we're going to use these splits. And, you know, the places where they might be slightly different is because, as I said, there are, you know, they do monitor the inputs at the fall lines. And, you know, there may be some small differences in the percentage of PIP to dissolve phosphorus or something like that at these different fall lines. So, as
Quick question,
Yeah.
sorry, Carl, for an interruption. I assume the fractions cyano and fractions diatoms, is that what that
Yeah.
Fs mean? And again, the difference, you have a third alkyl group?
yeah.
Okay, so since going back to the Susquehanna for a second, those are all 0, it means everything is going, the algae in the third group. Okay, so I understand. So why is the Potomac 100% cyanos coming in?
Because those are the fresh, well,
Oh, so they're-
there's a little bit of relic
Okay,
here.
all right.
What we have is a freshwater algal group.
Okay.
And what I'm saying is the Potomac is
It's fresh water.
it's 100% of that particular freshwater group
Okay, sorry.
because it's distinctive in the Potomac. So, you know, going down, basically speaking, we, for various fall lines or various places of entry, we have the option to use slightly different splits from these universal values.
So if both lines are 0, it means there's no phytoplankton loading right?
It means there are 3 groups, and we specify 2 of them. So if those are 0, then it must be the 3rd group. Okay. Okay, so now you can, if you wish to create your own set of loads for the bay, you can do it. Or I guess some of you might get, you know, you might be working on a subsystem. Somebody's doing a detailed model of the Chester River or something like that. You can, from here, using these numbers, you can get loads to the Chester River or something like that. You can also change those splits if you have better information, but if you want to use exactly what goes into the bay water quality model, you have it.